All right, picture this for a second. The exact millisecond a colossal lightning bolt strikes the outer jacket of a high-voltage cable. You've got millions of volts, thousands of amps, literally slamming into a material that is engineered specifically to stop it. So what exactly happens inside that material? Does it hold the line and store that massive energy, or does it violently short-circuit and catastrophically fail? I'm your host, and today we're decoding the high-stakes engineering mystery of what actually happens when an electric charge is forcibly introduced into a material.
Now you might be wondering, why do we care so much about this? Well, mastering the mathematical boundary between conductors and dielectrics isn't just some academic physics exercise. It is absolutely crucial for real-world design. Whether we're talking about preventing high-voltage cable blowouts, designing capacitors that won't short out, or shielding sensitive automotive electronics, you literally need to know exactly how charge behaves the very moment it enters a material.
So here's our quick roadmap for this explainer. 1. The atomic core theory. 2. A deep dive math derivation. 3. A real-world walkthrough. And 4. The engineering pitfall. Okay, let's jump straight into part 1, zooming in on the atomic core. To really understand how a material handles a massive surge of charge, we can't just look at the surface. We have to zoom way in, down to the microscopic atomic level. When an external electric field hits a dielectric material, the neutral atoms don't just sit there. The positive and negative charges get pulled in opposite directions, and they distort into these electric dipoles. Think of these dipoles stretching like tiny rubber bands under immense tension. They're storing energy, but they aren't snapping. Contrast that with a conductor, where free charge isn't tethered at all. It just flows freely and rapidly, kind of like a rushing river.
And to govern that rushing river of charge, we rely on the principle of charge conservation. This simply states that the time rate of decrease of charge within a given volume must equal the net outward current flow through the surface of that volume. In plain English, charges aren't magically created or destroyed out of nowhere. Every single electron that moves out of a space leaves a measurable deficit behind, and because of that, we can precisely mathematically track every single electron.
Which brings us to part 2, the math. And don't worry, we're doing a comprehensive equation breakdown.
Let's translate those variables into physical reality, and we are not skipping any steps here. Step 1 begins right at that conservation principle. The total current flowing out, we'll call that I out, is exactly equal to the closed surface integral of J dot ds, where J is the current density in amps per square meter. And this perfectly equals the negative change in closed charge over time, so negative dqn over dt. In step 2, we apply the divergence theorem, which lets us convert our surface integral into a volume integral. That leads right into step 3, giving us the volume integral of the divergence of J equal to the negative volume integral of the partial derivative of volume charge density, that's rho sub v, with respect to time. We are mathematically proving that surface flow exactly equals the volume decrease inside. So, drop the integrals and boom, we arrive at our crown jewel, the point form of the continuity equation. Del dot J equals the negative partial derivative of rho sub v with respect to t. Let's define this super explicitly. The divergence of J, meaning the current diverging outward from a specific microscopic point, exactly equals the time rate of charge density decrease at that exact same point. Now let's inject some real-world material properties into this. We start with our continuity equation. In step 2, we substitute Ohm's law, where current density J equals conductivity sigma times the electric field E. And we also substitute Gauss's law, where the divergence of E equals the volume charge density rho sub v, divided by permittivity epsilon. Step 3 yields our new equation. Sigma times rho sub v divided by epsilon equals the negative partial derivative of rho sub v with respect to t. Look closely at those two material properties for a second. Sigma, the conductivity, and epsilon, the permittivity. They physically act as the primary bottleneck for how fast charge can actually move.
All right, let's solve this differential equation. Step 1. We just rearrange it by moving everything to one side and setting it to 0. By separating the variables and integrating in step 2, we get the natural log of rho sub v equals negative sigma over epsilon times t plus our integration constant. Finally, step 3, we solve for our actual charge density, rho sub v. It equals the initial charge density, rho sub v0, multiplied by e raised to the negative t over tr. And look at that, it beautifully resolves into a clean, smooth exponential decay curve. The charge just drops off exponentially over time.
But wait, what exactly is that TR sitting there in the exponent? That, my friends, is our relaxation time. It's defined simply as permittivity epsilon divided by conductivity sigma. Relaxation time is the literal time constant, measured in seconds, that it takes for a charge placed in the interior of a material to drop to e to the negative 1, or exactly 36.8% of its initial value. This super simple ratio of permittivity to conductivity controls the entire decay process.
To really lock this in, here is the never forget analogy. Think of a really good conductor, like copper, as a highly pressurized water balloon. When you introduce charge into it, it violently pops, and the water, the charge, is instantly expelled right to the outer surface. Rapid decay. A good dielectric, on the other hand, is completely different. It's like a slow, multi-day leak in a super thick tractor tire. The charge takes a massive amount of time to rearrange and finally reach the surface.
Let's move to part 3 and put some numbers to this with a walkthrough of copper versus fused quartz.
Okay, let's test our water balloon analogy. We're going to solve a real-world numerical example methodically, just to prove that these formulas hold up to reality. Walkthrough setup 1 is copper. Straight from our text's material tables, the conductivity, sigma, is a massive 5.8 times 10 to the 7th Siemens per meter. Its relative permittivity, epsilon sub r, is exactly 1.
Let's calculate the relaxation time. Step 1, our formula. TR equals relative permittivity times the free space permittivity constant, epsilon sub 0, all divided by our conductivity. Step 2, we just plug the numbers in. 1 times the free space constant, which is 8.854 times 10 to the negative 12 farads per meter, divided by our massive copper conductivity of 5.8 times 10 to the 7.
When you divide those out, you get 1.53 times 10 to the negative 19th seconds. I mean, let that sink in. That is an unimaginably small fraction of a second. This mathematically proves why charge introduced inside a copper wire vanishes to the outer surface almost instantaneously. The balloon pops instantly.
Now, let's flip it and look at the other extreme. Walkthrough setup 2, fused quartz. It's a phenomenal dielectric. Its relative permittivity is 5.0, but look at its conductivity. Sigma is 10 to the negative 17th Siemens per meter. That is an incredibly tiny capacity to conduct any current.
So, we step through the exact same substitution. TR equals 5.0 times our free space constant, 8.854 times 10 to the negative 12th. But this time we divide by 10 to the negative 17th. And because we're dividing by such an infinitely small number, our quotient is going to absolutely explode into a massive value.
The result? 51.2 days. I mean, contrast that with the copper. If you introduce an electric charge into the dead center of a block of fused quartz, it will take over 50 days just for that charge to decay to 36.8% of its original value. The charge is effectively trapped. The tire is leaking incredibly slowly. This proves mathematically exactly why quartz is such a brilliant insulator.
All right, part 4, the engineering gotcha.
Before you go off and design a system assuming these extremes are absolute, you have to be aware of a very common pitfall. The danger is assuming materials are 100% ideal. The text explicitly warns us about this. Most dielectrics are actually slightly conductive, and most conductors are slightly polarizable. They aren't perfect. In real-world electromagnetic wave propagation, these tiny departures from the ideal cause real signal attenuation and phase shifting. If you ignore that slight conductivity in your dielectric insulation, I promise you, your high-frequency signal will degrade way faster than your models predict.
Okay, let's get into the summary and wrap this up. Let's do a rapid-fire recap of the 3 most critical takeaways you need for long-term retention. First up, the continuity equation. Del.J equals the negative partial derivative of rho sub v with respect to t. Current diverging out equals charge decreasing inside. Second, relaxation time. TR equals epsilon over sigma. The ratio of permittivity to conductivity is your master key to charge behavior. And third, that time constant physically represents the exact time it takes for the interior charge to drop to exactly 36.8% of its initial value. I'm going to leave you with a final, slightly provocative thought to chew on today. If all introduced charge rapidly vanishes to the outer surface of a perfect conductor in literally a fraction of a nanosecond, what exactly happens to the electric field inside that conductor? Really think about that. If you want the answer to that and you want to master more of the complex physics that drive our technological world, hit subscribe for more deep dive engineering survival guides. I'm your host, and I'll see you in the next explainer.